Okay, so with that, we're going to get an introduction to chapter 3. We're going to try to set something on fire, so at least it's worth our while to be here talking about this stuff today. And I know it's always a little bit obnoxious before a test to start getting into new material, but unfortunately, they wanted to put some of this material on the test, and so the best thing we could do is say, well, we'll stay caught up, but you just can't put what we're covering today on the test. So they were trying to put this on the test, so at least we were able to not get the chapter 3 first part of it on to midterm 1. And also I think a few of the details today may actually be helpful to start kind of putting together the thought of what these atoms do when we start thinking of molecules in terms of looking at some of their properties in terms of reaction. So chapter 3 gets into chemical equations or reactions. So the book always says chemical equations. I like to use the word reaction more. So an equation or reaction is like where we took 2H2 as a gas. You probably remember if you were here, parentheses, we blew up a balloon. And I thought about re-blowing it up, but we have already done this reaction here. But this is what we were looking at in the balloon, where we're doing a simple combination of the elements of hydrogen and oxygen into the molecule water. And so one of the things we have to do with the reactions, we have to balance out the left side, the reactants and the products, because we're just changing the form of two H2s and an O2 on average to make 2 water molecules. So we're just changing the environment for an average 4 hydrogen atoms and 2 O atoms into now 4 H atoms and O atoms, but in the combination of water into those new bonds into water. So we'll look at chemical equations, come up with a couple generalized reaction trends here in chapter 3. We'll look at formula weights, Avogadro's number, the mole, those topics here, empirical formula determination versus molecular formula, how we get formulas comes from chapter 3, and then also how we quantify aspects of reactions. Stoichiometry is by far going to be probably the one thing from 1210 that you keep seeing again and again and again is stoichiometry. But it's the one thing that hopefully by the end of chapter 3, if not once you start seeing it again in chapter 4 and again in chapter 5 and again a little bit later in the class, that it'll start to reinforce itself pretty nicely, I hope. So that's where we get into topics like how much product forms, what's the limiting versus excess reactant. You might remember some of those problems from past courses. Okay, so if we're thinking of this reaction, one of the things that I want to do when I write a reaction is I want to write usually the physical state. Now, it doesn't always mean that you can't always predict the physical state, but we had a balloon of gases. So H2 is a gas at room temperature, oxygen's a gas. Sometimes you know the physical state. If you imagine we blew that balloon up and went kaboom and with a big fireball, it didn't start raining anywhere, so water was being produced by a reaction that was so hot that it was just going into the gas phase and floating away as vapor. If we trapped it inside of like a container, we could probably condense the water if we wanted to make it in the liquid state, but water is probably just vaporizing into air before it has a chance to liquefy. So again, you can't always predict the physical state, but we like to show solid, liquid, gas here. Also, we'll show AQ in chapter 4 for aqueous. Mentioned that earlier, but we'll see that as a symbol that we learn more about in chapter 4 for things dissolved in water. And then we also want to make sure we balance our reaction. So the left and right side should have exactly the same atoms because we're not creating or destroying mass during the course of a chemical reaction. Now, a couple of categories of reaction we have are combination reactions, or things where we just combine 2 reactants to make a product. So a simple combination reaction are where we take our metals plus a non-metal element, and then we combine them to form an ionic compound. So sodium and chlorine reacting to form sodium chloride. I'm at that point with allergies right now where I can tell I'm probably going to lose my voice. So this is exciting. But 2 sodiums, 1 chlorine combining to form 2 NaCl's. Now I'm doing this balancing here probably first, so just noticing that I need 2 NaCl's to balance the chlorines. This is so simple. Let me not confuse you guys if I was being confusing. I'm kind of looking at my product has 1 chloride. I have 2 here, so I know I'm going to have 2 sodium chlorides to balance the chlorine atom. And then I need to put a 2 to balance the sodiums. So really straightforward balancing. Just balancing what we have to balance first, what we can balance first. We can predict the product like we did earlier. Aluminum 3 plus, oxide 2 minus is what we're forming. So we get Al2O3 as our product ionic compound from that metal aluminum reacting with oxygen. That's the only compound we can get between aluminum and oxygen. And so then how do we balance this one out? Because I have 3 here and I have 2 here. Well, I'm just going to have to use 3 here to give me an even number. So that gives me 6 oxygen atoms. And then I go 2 here, that gives me 6 O atoms. And then I have 4 aluminums, so 4 Al. So 4 aluminum reacting with 3 O2s, really basic balancing of reactions. Now, I have this memory of high school chemistry that I wish I could go back. Oh, no, I don't wish I can go back to high school. I almost wish I could revisit my notes from high school chemistry to see if this is true, but I feel like we balanced reactions for like 3 months. And I don't know if that was true or not, but I don't know if you guys had this experience too. But I feel like we were always balancing goofy reactions in like high school examples, and it was just like always some weird example after weird example. Our balancing is really straightforward. I mean, it's really easy to balance the reactions that we're giving you guys. It's like 1 page of notes. So we're just really just making sure you have whatever's on the left side balanced with whatever's on the right side of the reaction. And so we can have a decomposition reaction as kind of the opposite to the combination. So if you can combine things to make a common product, we can take a common product or a common reactant and break it apart into 2 or more products. So calcium carbonate can decompose into an oxide plus CO2, and that turns out to be a fairly general reaction. One, I don't know if you have to have this memorized, but metal carbonates when they're heated, we often use the symbol delta to imply heat. It means you heat up the mixture, then it forms the metal oxide plus CO2. And the calcium carbonate reaction is actually very much done in the production of cement. So you take calcium carbonate, heat it up to make calcium oxide, which is the key ingredient in cement. And so you're actually giving off CO2 anytime you make cement. You may not have thought that that the actual just like pouring of cement actually has a global warming possible aspect to it, or a CO2 man-made production of CO2 in the atmosphere comes from the building industry as well. So it's not just transportation that leads to CO2 being released in the atmosphere. It turns out building through like things like the release of CO2 from metal carbonates being decomposed, and those are an important class and common reaction done in the world. So I think about 5 to 10% of the CO2 production comes from this one reaction right here. Now, if we took a different metal like iron carbonate, which iron carbonate is that? Well, I know carbonate's a 2-, so this is 6-, this is 6+, so this is an iron 3+. So I can deduce the charge of iron carbonate here from the subscripts and the knowledge of carbonate being a 2-, so that's iron 3 carbonate. So iron 3 carbonate decomposes to form iron 3 oxide. And so that's going to be Fe2O3, and then going to form CO2 as a result. You could probably see that I'm taking the 3 CO3s, turning it into 3 O's, so I've lost 3 CO2s. So I've taken 3 CO2s off of the carbonates. So each carbonate loses a CO2. I've just lost 3 CO2s. And so this is in balance here. I have 9 O's here. I have 6 plus 3. I have 9 O's on both sides. I have 2 irons on both sides, and I have 3 carbons on both sides. So we're in balance. We should also be in charge balance, but this isn't something that comes up too often in 1210, but you should generally have, if you have all neutral things on the left side, you should have all neutral things on the right side, or just the summation of the charges should be equal. So if you have net neutral charge on the left, should equal the net neutral on the right side. Okay, so we should be in what we call mass and charge balance. So that just means our reaction should have equal charge and then equal mass on both sides. Now, combustion reactions are an important class of reactions, probably the most important class of reactions on this page. Hydrocarbon plus O2 to go to CO2 and water as a common reaction. And so we have methane plus O2 goes to CO2 plus water. So I have 4 hydrogens and CH4, so I need 2 waters to balance the hydrogens. And so then that gives me 4 oxygens on the product side, so I need 2 O2s. And then 1 CO2 is good to balance the carbons. So I don't need to write the ones per se, but that's the balancing for the first hydrocarbon. And then ethanol will burn with oxygen. We'll see an example of this in a minute. It'll combust with oxygen to form CO2 and water. If I do a 3 here for hydrogen, because I have 6 hydrogens, that gives me, well, let me also balance the carbons here, because I have 2 carbons. So I need 2 CO2s. And so then that gives me 4 oxygens plus 3. That's 7 O's on the reactant side. I have 1 here, so that's 1. And I can put a 3 here to give me the other 6, or the other 6 to make 7. So I have 6 plus 1, and I have 4 plus 3 to balance the O's. So just making sure we see that oxygen count. Okay, so let's take a look at that reaction here. So we have a carbohydrate that's filled with ethanol. Try to remember the safety glasses on this one. I'm not going to lie, it's actually more flammable than what it is. Okay, so we have ethanol in the container, and I'm supposed to do this to make sure that we have ethanol vapors in the container. I need to pour it out. Let me turn the lights down first. Reminds me of a YouTube video that I saw once. You guys see that one where somebody was making a video and lit their whole room on fire? That was cool. I'm glad I didn't say all that. All right, that was exciting. All right, so we just saw ethanol combust. so the ethanol was just combusting with the oxygen in air so that it could burn and form CO2 and water. So that was a demo on the combustion reaction of ethanol. Okay, so now we can predict the products of combustion reactions. So if we give you a hydrocarbon that contains CH and also O, we can balance the products to form CO2 and water. The only little details I like to mention, sometimes you can't predict what the physical state is of the alcohol. You may not, or the hydrocarbon, you may not know if it's a gas or liquid, so don't feel like you have to know that physical state. And then water can actually form, depending on the type of reaction we carry out, could be a gas or a liquid. And again, I wouldn't worry about that. CO2, though, is always going to be a gas. O2 is always going to be a gas in terms of their physical state in this reaction. Okay, let's talk about Avogadro's number for a minute. And then, so a mole is defined to be precisely 6.02214,076 times 10 to the 23. It used to be known, and we used to say that it was precisely the number of carbon atoms in an exact 12-gram sample of carbon. And like the way they define the numbers has just kind of inverted on itself from the way the IU pack determines the classifications, how conversion factors are determined. But it's if you think of a carbon-12 sample, remember how we said that carbon-12's mass was precisely 12 AMU for one atom? That if you had a 12-gram sample of that atom, you'd have an Avogadro's number of atoms within that sample. Okay, so a 12-gram sample of carbon-12, and precisely carbon-12, so not carbon in its natural abundance, but carbon of only being carbon-12 sample has this 12-gram mass. So there are this number of carbon-12 atoms in precisely a 12-gram sample, and this is of only carbon-12. And so what that allows us to determine is the mass of one of those atoms of carbon-12 in grams. So if you said I have 12 grams for all these atoms, all I have to do is divide by all those atoms, that'll tell me the mass of one of the atoms. So the mass of one carbon atom is taking the 12-gram mass of the collection, divide by all the atoms that there are, and just multiplying by the mass of one atom to get the mass of one atom. That works out to be a number that's exquisitely small, times 10 to the minus 23 grams. So when we start talking like the atomic weight of a gas, or the average atomic weight of an element, like carbon 12.0107, or whatever your periodic table says with the rounding on it. That carbon is like 12.01, that's taking into account the natural abundance isn't 100% carbon-12. But what this problem here allows us to see is that the mass of one of those carbon-12 atoms is 1.9926 ... times 10 to the minus 23 grams. One carbon atom is exquisitely small. Now, if you then go back to the AMU scale, if we said one carbon atom, what's its mass in AMU? It's very easy, it's just 12 AMU exactly. What's the mass of carbon-13? Approximately 13 AMU. If you remember our example is like 13.0037 or something like that. So only carbon-12 is exactly this number of AMU. And then if you said, well, what atom of carbon has a mass of 12.011 AMU? The answer is none. None of the atoms of carbon have that precise mass. It's 99% carbon-12, 1% carbon-13 in the natural abundance, in a natural sample of something containing carbon. In this example, we're saying just assume you have an object that's 100% carbon-12. So now what this scale here is doing is it's helping us devise the AMU to gram scale. So if we know the mass of one carbon-12 atom is this mass here, because that's the mass of one single carbon-12 atom, and then we know the carbon-12 atoms defined to have this mass of 12 AMU. So if I say, well, that collection of grams, that's just 12 AMU. We're just going to agree that that's 12.000 out to infinity AMU. Then we're defining this mass here is equal to 12 AMU, just exactly. And then we set this mass here equal to 12 AMU exactly. Allows us to determine that 1 AMU, if we divide both sides by 1.99264 ... times 10 to the minus 23, so take 12 divided by the number here, we get this conversion factor, that 1 AMU is equal to 1.6605 ... times 10 to the minus 24 grams. So you see that AMU to grams, and this isn't just for carbon, this is for all things, that you can convert grams to AMU, AMU to grams, just with this conversion factor. So AMU to grams, it's just like grams to kilograms or pounds to kilograms. It's just a simple conversion factor. It's just a conversion factor that shows you the AMU is a really small number of grams. 1 AMU is a exquisitely small collection of mass. But then if you divide both sides by this number, if you say, well, just invert, if you just took 1, in fact, this is somewhat fun to see. If you just take 1, divide by 1.6605, 39067 e to the minus 24, that you get Avogadro's number. That the conversion factor between grams, I mentioned this earlier in the class too, that the 1 gram in AMU is Avogadro's number. Now this is very useful because what this is telling you is that if you know the mass of one carbon-12 atom is 12 AMU, mass of one carbon-12 atom, if you said, well, what's the mass in grams per mole? What's the molar mass? What's the mass of an entire mole? Well, what we would do is we would say, well, to go AMU to grams, if I'm trying to convert this into grams per mole, then I take my 12 AMU is the mass of one carbon-12 atom. I just take my AMU conversion to 6.022 ... times 10 to the 23 AMU per gram. So that cancels out my AMU. And then I do my conversion that I have 6.022 times 10 to the 23 carbon atoms in 1 mole. So a mole is defined to be that number of things. So a mole is just 6.022 times 10 to the 23 of whatever the thing is. So you can have a mole of carbon-12 atoms. You can have a mole of H2 molecules. You can have a mole of CH4 molecules. You can have a mole of glucose. You can have a mole of whatever the thing is. It's just like you can have a dozen eggs, or you can have a dozen of pairs of things. You can have a dozen collection of things. So you have a mole of an atom, you can have a mole of a molecule. So here we have a mole of atoms, and so 1 mole of carbon is just 6.022 times 10 to the 23, the same number. So you get that the molar mass of carbon 12 grams per mole. So the AMU to molar mass scale is such that it's the same number. And this works for all things, not just carbon, that if you know the molecular weight, there's a slide on this in a minute, but the molecular weight is just from adding up the masses. Like let's take water, for example. So if you take water, 2 times 2.016 from the periodic table for hydrogen, or 2 times 1.008, which equals 2.016. So take 2 times the mass of hydrogen plus the mass listed for oxygen is 15.9994. I usually go to 2 sig figs for lecture problems. So you usually see, or 2 decimal places, and then 3 for hydrogen. You'll start to get that we're usually going for about 4 total sig figs on a molar mass. But if I add these up, I get 18.02 AMU. That I can add these up in terms of their atomic mass unit. So the mass of 1 water molecule in AMU is 18.02 AMU. Now, what about grams per mole? Well, AMU to grams, Avogadro's number. Like 1 water molecule to an Avogadro's number to a mole is also Avogadro's number. That this would also be 18.02 grams per mole. So grams per mole AMU, not synonymous with each other because they're different things. This is the simplest but hardest to grasp concept I think in chemistry is this, that the AMU is the mass of just 1 single atom. The gram per mole is the mass of a collection of atoms. It's the grams per an entire mole of the collection, but they have the same number. 2 different things, so they're not the same unit. So we're not saying 18.02 AMU is equal to 18.02 grams per mole. We're just saying that they have the same number. And it's useful that they have the same number because we can treat the masses on the periodic table as the atomic weights in AMU, the average atomic weights, or the average molar masses. We could also have just said that these are the grams per mole of those elements. So you'll see us thinking grams per mole or AMU or interchanging these units a lot in this chapter, but we're going to start dealing with more than just 1 atom. I think it's useful to think that for whatever the element is, imagine chlorine. Chlorine's 35.453 or whatever, 35.5 AMU is its average atomic weight. And there's 2 isotopes of chlorine, 35 and 37. So the average of chlorine is coming from 35.0 versus 37.0. And you can sort of tell it's more the 35 because the average atomic weight's closer to the 35. But the average atomic weight of chlorine, no atom of chlorine has that mass. It's either 35 or 37. It's kind of getting the thought that chlorine, even though it has an average atomic weight of 35.5, that it's still either this isotope or that isotope, never the actual average. And so using the periodic table is what we really want to learn how to do. We're usually dealing with the natural samples of these elements as they form compounds. We want to use the average abundance of a given isotope, since that's the form we're going to be dealing with things in the lab. When we get a sample in the lab of something that has carbonate, it's going to have the natural abundance of carbon within that sample. That's the number we want to use, is the average abundance for the given atoms. So calculating molar masses versus molecular weights, just a little bit of the lingo here for C2H2, is that the molecular weight I usually tend to think of as being the AMU, and I usually think of that being per molecule. And then the molar mass, this is my grams per mole. It's kind of implied in the name, the molar mass, the mass of a mole in grams. And so for C2H2, this is going to be 2 times 12.01 for carbon. And I'm going to think AMU first. It doesn't matter how you start this problem, but 2 times 1.008 for hydrogen. Adding these up, I think it's 26.04, but let's double check. Yep, 26.04. So we can say one molecule of C2H2 has a mass of 26.04 AMU. We can say then that the molar mass would be 26.04 grams per mole, because the AMU to gram conversion and then the per atom to mole conversion is the same numbers. We're just multiplying and dividing by the same number. So it's 26.04 grams per mole. And then we can compare, and we can even calculate the mass of one molecule in grams versus AMU. So one molecule in AMU is 26.04 AMU. The mass of one molecule in grams, so that's the mass of one molecule, is just 26.04 AMU. Let me write this more clearly. And then my conversion factor for AMU into gram, the one I like to use is that there's an Avogadro's number of AMU in a gram. So it's 6.022 times 10 to the 23 AMU per 1 gram. So if I divide 26.04 by 6.022 times 10 to the 23, I get 4.324 times 10 to the minus 23 grams. So obviously a really, really small mass for one molecule. Okay, so we can compare masses of one molecule. Now we're going to predominantly work with molar quantities, so noting that there's 26.04 grams per mole is probably going to be a number we use more frequently as we continue into the chapter. And so we can also look at formulas. So what's the difference between C2H2? This is a molecular compound. K2SO4 is an ionic compound. And now the real distinction here, and this is an important one, is that C2H2 being molecular, if I had acetylene, that an acetylene molecule is different from its neighboring molecule. That you're going to have a collection of acetylene, you have a bunch of C2H2s. The way it actually looks, and you don't have to predict this structure, but it actually looks like this. You end up with a bunch of these molecules that are all independent of the molecules next to them, other than maybe there's some interactions. Maybe if you have a liquid of the sample, it would, there'd be some intermolecular forces between the molecules linking them together. But C2H2 turns out to be a gas at room temperature. So there really isn't too much going on in a sample of acetylene other than a bunch of individual molecules that kind of look like this structure here, versus K2SO4, which is, most of our ionic compounds are solids at room temperature because they have such strong ionic forces of attraction. And then you just get one compound that forms with this ratio of 2:1 for K plus 2 of them to sulfate ion. So that's potassium sulfate. And so the main lingo difference here is that I don't have a molecule for this one. So I tend not to talk about molecular weights for K2SO4, but most people do in lingo talk and say the word, what's the molecular weight of K2SO4? So in lingo, you'll see people and still see that number reported, but it's really a formula weight. Usually with things that are ionic, we tend to say, well, let's just give the formula weight. And it's exactly what you'd expect. It's just 2 times potassium mass, which is whatever it is, 2 times 39.10. And then plus 32.06 for sulfur, and then plus 16.00 for oxygen, and there's 4 of them, so times 4. So looks like the molecular weight, but the key is it's just not a molecule. It's like a unit. So we call that a formula or a formula unit. So 2 times 39.1 plus 32.06 plus 16.00 times 4 is 174.26. And again, it'd be AMU or grams per mole. So AMU for one of those units, or the grams per mole for the molar mass. Now, as I think about the percent mass, the percent by mass of carbon, let's actually get into this after our test. So we'll come into this slide here. We'll go through like breaking down a water sample and trying to figure out how many moles there are in the sample and how many water molecules, et cetera, there are. So we'll pick up from this after our test. Good luck on the exam, everybody. I have office hours today, right after class till 10. Check those out, and I'll see you Wednesday.